We are going to thoroughly discuss the ARIMA model, which stands as a significant and widely utilized technique within the comprehensive framework of time series models. As is our usual practice, we'll be navigating to the Finance Research Gate website to kick off our session today. But before we proceed, it's essential that we take a moment to refresh our collective memory on the basic terminology. ARIMA, as you may recall, is the abbreviation for the Autoregressive Integrated Moving Average Statistical Model. So, in this particular analysis, we're presented with three distinct components that we absolutely must identify. The first is the AR part, which is known as the autoregressive element, and this is precisely what effectively captures the underlying momentum and the variable movement within the data. AR here is referring to the fundamental consideration of whether we have to perform the integration and subsequently ensure its stationary nature. So in some instances, the fundamental level of the variable may not be truly stationary. Therefore, the ARIMA model will first supply a differencing step to the series before integrating the autoregressive and moving average components. The MA, or moving average, represents a crucial statistical calculation. It specifically points to the unexpected error shocks or disturbances that are instrumental in clarifying short-term fluctuations observed within the particular variable under consideration. So this is what the ARIMA actually looks like. The current value of this particular variable is directly determined by its own past values following an autoregressive path, which is specifically linked to the parameter p. Furthermore, this particular component represents the innovative aspect, capturing the new and unpredictable elements within the system. Consequently, previous shocks or disturbances can indeed carry a significant and lasting effect into the subsequent period. We are asking about the number of past time periods or the extent to which previous innovations are expected to influence the current level of XA. This information will be provided by the Q parameter. It also determines how far back in time we can trace the impact of various error shocks. So the resulting error that we obtain from the application of this particular equation, or more precisely, from the process of fitting this mathematical model to the data, should, in theory, average out to exactly zero. This clearly indicates that our model has been successfully implemented and applied. So typically we employ the ARIMA model when we're analyzing data where the variable isn't stationary, such as the overall price level. If we're dealing with a stationary variable, such as returns, and it's quite likely that these returns are stationary, then we can proceed to apply the ARIMA model. However, we did state that d should be equal to 0. So in this particular context, the variable d that we are discussing here, it actually represents the I component. This I part is crucial because it helps us to precisely determine the specific order of differencing that we will need to apply when we are trying to identify the variable. For example, are we looking for the first difference, or perhaps the second difference, or even further differences and so forth? So for example, if I were to say 1, 1, 1, what that would then mean is that we are going to be utilizing just a single lag of x, and we are going to perform a differencing operation on the variable, and then we will proceed to set one lagged innovation or error term. So in this particular instance, if we are working with a variable such as xt, the very first step we need to perform is to calculate the overall variation, which is commonly known as the first difference, that initial change between successive points. And this particular item right here, this is the one we're focusing on. Then moving forward, let's just refer to this specific thing, for instance. And then we're going to model the differenced variable in two parts. Let's say this is the constant plus. We'll be utilizing a single autoregressive term within our statistical framework, and this specific element is intended to thoroughly explain this particular portion of the data. Additionally, we are also planning to incorporate just one component from the moving average model. The calculation involves taking theta and multiplying it by the previous innovation. Also, we are now examining the inherent error of the statistical model. So this particular section will clearly represent that crucial component. That's precisely how the ARIMA methodology operates and performs its calculations. Once we have successfully set up the ARIMA model, we will then proceed to carefully examine the residual. Following this estimation phase, it's essential that these residuals are carefully checked for any remaining serial correlation. We shouldn't have any serial correlation remaining. If we have any remaining serial correlation, it means that we did not successfully model the autocorrelation in the variable of interest. Additionally, it's quite important to assess the data for its normality and also to look for any significant variance effects, such as volatility clustering. We should note that the ARIMA model specifically addresses mean dynamics only. It primarily explains the overall level, the average level of the variable. It does not, however, account for or model any volatility. So it could be considered quite normal, for example, that after applying the ARIMA model, the other one might then clearly exhibit some significant volatility clustering. That is quite normal, as the ARIMA model does not directly account for the volatility of the variable of interest. It's primarily a mean dynamic model. So, for example, if we are considering this ARIMA model, a value of 0 in this context indicates that we do not need to perform any differencing operations on the variable itself, neither the first difference nor any subsequent x-order differences.
Here we are using two autoregressive statistical models.
And also incorporating a single delayed innovation term within our model. Considering all of these established parameters and taking into account the specific value of x, along with the previously observed lagged value of x and the associated lagged conversion factor, we are then able to precisely determine the anticipated or projected level of our dependent variable. And that would be, for example, in our specific case, a value of minus 0.22. If the actual realized return is minus 0.1, this means that the error represents the true value minus the one expected from our model. We have the model for which we determine the expected value, and that particular result will then represent the error in this specific situation. In this specific situation, the model's forecast indicated a much stronger reversal than what actually transpired. Its prediction was a decline, specifically of negative 0.22. However, that predicted decline was actually lower than the actual observed decline. Therefore, we can conclude that there was an overproduction of the reversal in the model's output. So, we're going to take this concept and apply it directly, making use of the Finance ResearchGate website. From there, I'll proceed to select the specific time series data. And then for the frequency, I'll be choosing the monthly setting, and I'm going to make sure that it's set to conclude by the very end of December of the year 2024. Apply. The variable that we have decided to select for our analysis is the current oil price.
Let's consider the price of West Texas Intermediate crude oil, which is a key benchmark. The API gravity measurement here specifically reflects the density, showing how heavy or light the oil is.
So, this particular metric serves as a very reliable benchmark for crude oil. It's always quoted in terms of the US dollar price for a single barrel of this commodity.
And here we can clearly see the mean value.
We're looking at oil price data on a monthly basis, covering the extensive period from 1962 all the way up to the year 2024. So after you finish selecting the Apply button, the system will then proceed to implement the chosen variable of interest. And right here, if you look down, we have the chart displayed. It clearly indicates that the collection of data commenced back in the year 1992. Therefore, this is a complete set of information we currently possess. As we can readily observe, the price level of oil is clearly not stationary in its movement because we consistently detect a significant underlying trend. This directly means that its average value, or the mean, is certainly not constant over any given period. Also, if you examine the autocorrelation, the figures indicate they are extraordinarily high, far exceeding our initial projections. For example, the first lag is very close to 1. This strong correlation also persists for lag 2, lag 3, lag 4, and lag 5. In fact, even when we extend our analysis all the way to lag 12, we still observe a highly significant autocorrelation. So, the autocorrelation function, or ACF, is consistently remaining very close to 1 across the majority of these observed lags. This specific behavior is a classic and highly indicative signature of a unit root process, particularly when you encounter such a persistent and substantial amount of autocorrelation extending back through a considerable number of prior lags. The PCF, as we've discussed in our previous videos, provides crucial information regarding the additional explanatory power it offers at each successive lag. Specifically, it helps us understand, after we've accounted for the influence of the first lag, precisely how much autocorrelation is still present, originating from the second lag. It is significantly lower than the autocorrelation function because in this specific scenario, we are carefully accounting for any potential intermediate time delays or lags. This ensures that what we observe is a very clear and distinct drop. However, when running the ARIMA model to decide which is the best ARIMA model, it is crucial to deal with the stationary variable when we examine the autocorrelation diagnostic. So in this particular case, we are going back. In order to generate a new data series, we should proceed by choosing the appropriate time series transformation. And for the purpose of clear identification, we should name this specific component difference series. We need to allow just a little bit of time for that to process, and then once that's done within this designated selection box, we'll proceed to choose the very first difference. We are creating a new variable that would take the first difference. This is exactly the scenario we're examining. Our process involves taking the previous or lagged data point and subtracting it directly from the current observation to obtain what we call the differenced variable.
All right, we finished up everything we needed to do here. Now let's head back to the main chart, and then we'll incorporate the new data series we just created.
I'd like also to take a very close look right here to ensure that we are not observing any kind of significant underlying trend in the data. And then, following that, let's also carefully examine the autocorrelation results. This particular one that you see displayed here is indeed the original version. This represents the current updated version. Now, we can observe that the autocorrelation is indeed significant at a lag of 1, but it is certainly not close to a value of 1. Instead, its actual value is approximately 0.33. What this indicates is that at that specific lag value, we can expect to account for roughly 33% of the total fluctuations seen in the overall price. When considering the second lag, it is evident that its observed value lies entirely within the defined boundary of statistical non-significance. So if they're really close to the point where we would consider them to be statistically non-significant. For lags 3, 4, and 5, their values all become very close to 0. However, there is one clear exception to this trend, and that is lag 6. But generally speaking, for all of the remaining lags after the initial lag 1, we observe that there is no significant correlation. And then if we proceed to examine the partial autocorrelation, what we're observing is a distinct trend where we encounter a notably significant level of autocorrelation specifically at the first lag. However, as we then examine subsequent lags, such as lag 2, lag 3, and lag 4, we find that their respective values consistently diminish and ultimately approach a state very close to 0. So the crucial question is, how can we accurately determine the correct ordering for our ARIMA model? We've already established that the D parameter in this specific instance must be equal to 1.
We should be the first to notice the main difference.
Now, what about the P and the Q parameters? How many autoregressive terms should we consider for our model? Well, the general rule of thumb that's often applied here, or as it's frequently referred to in various academic cases and within the Box-Jenkins methodology textbooks and readings, is quite specific. If both the autocorrelation function ACF and the partial autocorrelation function PACF exhibit a tailing off, we then fit an ARIMA model. This involves carefully selecting appropriate values for the parameters P and Q. But if one of them begins to tail off and the other one then cuts off, it effectively means that one of them will receive absolutely no value at all. Now, in this particular case, the autocorrelation function, or ACF, shows a strong, clear correlation at the first lag, but then this effect quickly diminishes, becoming less pronounced by the second lag. So we're observing a process of gradual decay. It doesn't abruptly cease right away. The second lag is practically negligible, almost at 0, and therefore not truly significant given its proximity to the boundary line. It is sitting right there exactly on the line, so that could potentially be quite a bit significant. So what we have here is a gradual tailing off. We don't have a very clear cutoff point. However, looking at the PACF, we see a very clear cutoff right after the first lag because the value for the second lag is so close to 0. So that specific pattern where you have a clear cutoff after the PCF, but then a gradual tailing off for the ACF indicates that we are primarily dealing with the AR approach, not the MA model. So for this particular scenario, we're able to set this specific parameter to 0, meaning there's no moving average component, and then we can set that other value. What exactly should that value be in this situation? It really should be 1, because we are carefully examining the partial autocorrelation. Once we've accounted for the first lag, it's clear there's no direct influence coming from subsequent lag, such as 2, 3, 4, and so on. Therefore, a single lag is entirely sufficient. Our model will then be structured in this specific way. After performing the initial difference calculation, the outcome is a constant value. Perhaps it wasn't the most ideal decision to choose this particular symbol for our current representation. It might lead to some confusion later on. Therefore, we have the option to simply pick an alternative, such as the letter N, which is quite common and clear. And then regarding our current setup, we'll have 5 distinct units, each associated with a specific lag term denoted by the variable W. Once those elements are firmly established, our configuration should be complete and perfectly adequate for our purposes. That will be the specific model that we are going to be fitting and applying within the context of our current case. In order to properly perform the ARIMA process, we need to scroll down to the classical time series analysis, and one of the available options we have is the ARIMA model. So let's select the appropriate model. At this stage, we are selecting the original data series, as the ARIMA model will perform the differencing of the variable for us. So we select the original data, but we must ensure that we select the differenced. Thus, the ARIMA model will first difference the variable, and then it's fed into the AR component. Now, concerning this specific part, as we've already discussed in our prior conversation, we fully expect that there will be no A component present here, and therefore we are going to set its value to 0.
And let's go ahead and call this
the captivating visual experience of ARIMA.
Of having a single autoregressive term, meaning the current value depends on the previous one, and also incorporating a single order of differencing to achieve stationarity, while crucially having no moving average component whatsoever. And then, with these specifications, let's proceed to fit the model. Here the coefficient is quite significant. It's a crucial element. We are finding that approximately 1/3 of all price changes can be attributed to the lag effect. We are focusing on the specific price movement of our designated variable. Consequently, all the numerical figures that you observe displayed right here are directly linked to this particular price change variable. And it is quite significant because the z-value itself is highly significant. Its actual value is 4.5. The p-value is so small. So in this particular case, if you look back at the information we've discussed, the numerical coefficient for this variable, pi, is exactly 0.33. To clarify, the specific notation we're using here, sigma square, is precisely defined as the variance of the residual or error term within our regression analysis. And it is quite significant, and that is entirely expected because the measurement errors here will certainly fluctuate over time. If we take a close look at the statistics presented here, all of which are directly linked to the error term within our model, it becomes clear that the errors themselves, they are not demonstrating normality because the Harke-Berra test has yielded a significant result. Consequently, the null hypothesis stating a normal distribution of the error term can be confidently rejected. The most crucial aspect that we absolutely must take into consideration here is the autocorrelation of the error terms. This autocorrelation is not statistically significant, which clearly indicates that our predictive model has successfully captured the inherent autocorrelation of the primary variable of interest, because the error, which represents a portion of the data not yet explained by our model, does not exhibit any autocorrelation. This absence of autocorrelation is in fact a very positive characteristic for the overall robustness of our model. If our model, for some reason, still exhibits autocorrelation within its errors, it clearly indicates that we are overlooking some important aspect. We might need to revisit our current approach and incorporate additional terms. For instance, we could consider including the moving average component. After that, we can make a forecast. And then we can proceed to generate the forecasted values, all derived from our established model. So this is simply the model that we are working with. We're employing a single autoregressive model specifically for the price changes of crude oil. These figures here represent the forecasted values. The key question is, how do they compare against the actual observed values? We were examining, for instance, the root mean squared errors here. To calculate this, we first square each individual error value, then we proceed to compute the average of those squared errors, and finally, we extract the square root of that average, which ultimately yields a result of 4.7. We need to remember that the higher the value, the worse the model's overall performance is. The current reading is 4.7. Additionally, we're looking at the out-of-sample descriptive statistics. It's quite typical for the out-of-sample performance to be worse than what we see in the in-sample data, because the out-of-sample metrics will naturally show a higher, less favorable number. This is primarily due to the fact that the underlying model itself can evolve and change over time. So we are going to be using all of the available periods except for the final 12. So, when we're training and fitting the model, the forecasted period that's displayed here, which amounts to a total of 12, is going to be used as an out-of-sample test. And then, what you're seeing here is the performance of our model when it's outside of the sample data. If we were to alter the current setup, perhaps by adding an additional moving average term, the resulting model could either be an improvement or a detriment. Therefore, it's generally not beneficial to over-parameterize the model. For instance, if I were to fit the model in this specific context, I completely forgot to share this. Then you can clearly see that none of the coefficients, in fact, are statistically significant at this moment. Neither the AR, which stands for autoregressive, nor the MA, the moving average.
Why? Well, it's because we allow a competition to take place between the MA and AR terms when trying to explain the short-run structure of the data, and this in turn over-parameterizes the entire model, ultimately making its performance significantly worse.
So that's it for the ARIMA presentation. Thank you for listening.